Welcome back. This is part 2 of our discussion about the existence of Euler's number, E. In the first part, we got to the point where I said we really, right now, because of the theorem that we have, we really only need to prove these two statements. Then we'll use that theorem to prove that the number E actually exists. Okay? And so, just to be clear, the two things that we're trying to prove that this is true for all integers n. N has to be an integer because we're talking about a sequence here. And it needs to be a positive integer. Also, you could see right here that n cannot equal 0. Okay? You can't plug a 0 into there, so obviously what we're talking about is that these two statements hold for any integer n where n is bigger than or equal to 1. Okay? Those are the two statements you're trying to prove. And last time, I gave you a little hint for some ins and outs on how to do this, and I told you that we would start today with two big hints. Okay? So here's the first hint. Here's hint number 1. Hint number 1. Use the binomial theorem. Which, remember, if you recall, we have a video on this, if this is alien to you. The binomial theorem tells us that for any two real numbers, x and y, x plus y raised to some power, any power, let's call it n, and I think it needs to be a positive power the way we did it, raised to any integer n, it's equal to the sum as, and I'll use a dummy variable k, as k goes from 0 up to n of n choose k, and if you remember n choose k, I'm going to write it in factorial form, which is n factorial over k factorial times n minus k factorial. Okay, so that's what this is, n factorial k factorial n minus k factorial times it's x raised to the n minus k and y raised to the k. And remember, because this is symmetric, right, that y plus x is the same thing as x plus y, then we could flip these around. You could write this as x to the k, y to the n minus k, or you could write them in the opposite order too, and it's still true, right? There you go. You could write it any of those ways, and it's still true. One of those ways, given what you're trying to prove, will make your life much easier. I'll leave it to you to decide. Maybe you want to try both ways, whatever. But here's your first big hint. So you will need this for both of these right here. Okay? So I recommend that you stop the video and work on this for 2 days. Okay? Like really just use this hint, spend 2 days, and I don't mean 48 full hours. I mean like work on this for a while, put it away, work on it, and do that for a couple of days. And then if and when you still are having some trouble, come back, start the video over, get up to this point, and then come back for hint 2. Okay, but don't keep watching. Stop the video right now because I'm about to put up hint number 2. Okay? Here's your last chance to stop the video because I'm going to tell you hint number 2 right now. Are you ready? Okay, so you've spent the last couple of days with hint number 1. And here's hint number 2 if you're still having problems. Induction. That is mathematical induction, like we talked about in class, right? Induction will not help you. If you're like me, you spent a very, very long time trying to use induction to prove this because you'd think that it would, right? You would think Like it lends, it's you know, you're trying to show that something's true for all the integers. It has this flavor, like, and so you think, okay, well, we'll just establish this, and then the next case, we'll just use this to prove the next step, which would be you add 1 to all these, right? And 1 plus 1 over n plus 2 raised to the n plus 2, right? You'll do that, and it should work, right? It should be no problem. It's a huge problem. Good luck trying to do that. It's never going to work. It's... Especially because if you did follow hint number 1, you had something like this, right? You have k goes from 0 to n of n factorial k n minus k. And depending on how you did it, you probably ended up with a 1 over n to the k. And over here you have this. And if you did this right, you'll have n plus 1 right there. N plus 1 factorial k factorial n plus 1 minus k factorial 1 over n plus 1 to the k. And there's a few problems here if you've been messing with this. Like, if you're trying to do induction on this, like this is what you're taking as your true step, but now you need to show it's also true in the next step. And you have a few problems, like yes, you have 0 up to n. You have a total of n plus 1 terms over here. Like 1 plus all the way up to something. There's a total of n plus 1 of these. On this side, you have 0, 1, 2, all the way to n plus 1 would be a total of n plus 2 terms. And it's like, oh, that's nice. But a bunch of these end up being smaller than those. And so then you're trying to show in the next step, in the inductive step, well, what do? I'm going to try to add something over here. The thing you would need to add would be the next step. And then the thing you need to add over here is the next step. But this one's bigger than that one. It's just a mess, and you could spend, as I did, an embarrassingly long time trying to use induction for this. Now, before I tell you to turn the video off and go use hint 2, I will say that if you I'm saying induction won't help. It doesn't mean that you won't use induction at some point. But it's not for the big picture here in either of these. You're not going to say, in the base step, it's true when n equals 1, and blah, 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 blah. Rather, you're going to do a whole bunch of work, and whichever one of these you want to do. Maybe here's a hint 2.5. Do this one first. It doesn't matter. I mean, that you don't need to. You could do this one first. It's fine. It's just that when we go to prove this in just a minute, I will do this one first. Either one works. But what I was saying is that with there is a point as you're doing your work that you're going to need to use something, and to show that that's true, technically you need induction to show that this little part of it is true. But it's so obviously true that if you didn't use induction to prove that little step in there, I would forgive that. I'd be like, yeah, okay, it's obviously true. But if we wanted to be absolutely rigorous, you would want to prove that, and we will. But when we get to it, I'll tell you, like, you know. Well, you'll see when we do it. So in other words, you're going to go through and get to a point with one of these where you're like, well, oh, this is less than that. But in order to actually show that one line is less than another, technically you would need an induction proof. It's obvious that one thing is less than the other. And so if you want to just breeze through that, that's fine. So, but the hint number 2, that induction is not going to help you, don't let that dissuade you from that little part in there where if you want to use induction to show that this one step is less than that. The big hint is that you don't want to do an induction proof on this thing. because it's not going to help you. It's if you've spent the last 2 days trying to use induction, good. Like that's what I did for, I'm not going to tell you how long, a very long time, just trying to do induction on this thing and trying a bunch of different ways of writing it and doing induction, and it just, no fruit. It just gave me no fruit at all. And now it's possible that you could, I suppose, I'm sure some genius could say, I'll do an induction proof and put it up, and I'm like, oh, that was obvious. Why didn't I see that? But I'm telling you, induction ain't going to help you here. So those are your 2 hints, okay? Now that you have this next hint, maybe you need to start thinking about this differently. Like, you're looking for a direct proof. And I'm going to go ahead and recommend that you just start with this one. Because if you get this one, it will open your brain, it will open your mind, and you'll go, ooh, I could do the same thing I did there with that one. And it's not induction, it's just a direct proof. Use the binomial theorem and try to show that this thing is less than some real number m. So go work on that for 2 days, then come back. So the first statement that we're going to prove is this one right here. And in particular, what we're talking about is we need to show that there is some real number m such that for all n bigger than or equal to 1, like we said, right, this is true. In other words, that this sequence is bounded above. It has an upper bound, m. And I said, the hint I gave you was, the most important one, was that we need to use the binomial theorem. So I said we need to use induction. No, don't use induction. That's a problem, right? Okay, so we need to use the binomial theorem. Okay, so what I'm going to do, and like the other hints I gave you, is you should just take this and try to manipulate it until you get a real number. Say like, you know, this thing is less than something else, which is less than something else, blah, 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 which is less than, and I told you 3 is going to work, and in fact, that's what's going to pop out, but we don't know that yet, so forget about the 3, okay? So that's what we're trying to do right now, and I told you use the binomial theorem. So let's just start with the left-hand side and use the binomial theorem. So I'm going to say, okay, 1 plus 1 over n raised to the n is, by the binomial theorem, the sum as k goes from 0 up to n of n factorial over k factorial times n minus k factorial times 1 to the n minus k times 1 over n to the k, but 1, this is the nice thing about having it written like this, 1 raised to the n minus k is just 1, so we don't need to worry about writing it. I'm just going to leave that and write this as 1 over n to the k. Okay, what do we do from here? Well, the first thing I'm going to do, I don't like this 1 over n raised to the k, and I don't like having it separate from this thing that I'm trying to work on, right? This is called the summand, the thing that's in the sum, the thing that we're actually doing. So I'm just going to rewrite this like this. I'm going to say, okay, the sum as k goes from 0 up to n of n factorial, k factorial, n minus k factorial. Now, that 1 over n to the k is the same thing as 1 over n to the k, right? That should be obvious. And I don't have to have it times that fraction. In fact, I'm just going to go ahead and put him down here in the denominator. I'm going to take that n to the k right there. Check me on that. Does that work? Yep. Okay, so that's the same thing right there. I haven't changed anything. Okay, now what? Well, there's a lot of things we could do. I know that what I'm trying to do is make I need to show this being less than something else, right? And that's the idea, is if I could just manipulate this. Ooh, one thing, and hopefully this just popped into your head. Probably didn't. But I've been hinting at this for a long time, and in fact, in a quiz, there was an extra credit problem, and I'm hoping that all of the seeds that I've been planting over, at the end, especially at the end of the year, last year, that when you saw this, you're like, well, if I need to rewrite this, and I have n factorial, and I have this n minus k factorial right here, you probably did a lot of different things. You could write this a lot of different ways. What I'm hoping is that at some point you were like, well, maybe I'll just write this thing out. This is n times n minus 1, n minus 2, all the way down to say like n minus k plus 1, n minus k, n minus k minus 1, all the way down to say 3 times 2 times 1. That's what n factorial looks like on the top. You have your k factorial down here. You have your n minus k factorial, which is n minus k minus 1, all the way down to 3, 2, 1. And that's times your n to the k. And I really harped on this a bunch of times, is that you could rewrite this, right? Cancel all these guys out, so that this is the same thing as n times n minus 1, n minus 2, all the way down to n minus k plus 1 over k factorial. In fact, that's how we derived this thing in the first place. Or like that was the whole point. Remember when we first talked about n choose k? Like this was what we defined it to be. If you have n things and you choose k, if you have a total of n things, how many ways are there to choose k things out of them? It was this. The only reason that we brought this guy in there in the first place was to rewrite n choose k in a way that only involves factorials. Because you can't, this does not involve factorial. This is not a factorial over a factorial, right? And so, in a sense, this is the pure n choose k. This is what n choose k is, okay? And in that extra credit problem I had, I said how many, and of course the way I wrote, I could have written it a lot better, but I said how many things remain on the top? How many terms are there? There's the n, there's the n minus 1, there's the n minus 2, and when you count them up, there's a total of how many of them? There are k of them, right? A few ways we could see that is the number of things up here are n. The number on top is n. You have k, so there's k terms in the k factorial. How many are in the n minus k factorial? Well, there's the number of them is n minus k. That's what it is. And so now you've subtracted off n minus k of these things. So in other words, you had a number of n things, and you subtracted off n minus k things. That's the same thing as taking n minus n plus k. How many things remain? Well, there's k of them remaining. So there's k terms up there. The other way, the really abstruse way that I did it when I explained this was this last term is the same thing as n minus k minus 1. And so you have 0, 1, 2, all the way to k minus 1. How many is that? Well, k minus 1, but then you add in the 0. It's a total of k of them. I'm really beating this dead horse because I don't want this to look like magic. I want you to remember this, right? Not just going forward, but I want you to recall that we did this a bunch of times. And I was trying to plant this seed because this whole time I've been waiting for this moment. I've been waiting for this moment. And I want you to believe that we could do this, that we could rewrite this thing as this. Okay, it goes from 0 up to n of n minus 1, all the way down to n minus k plus 1 on the top. Down here we have k factorial. We've canceled out the n minus k factorial. That's how we were able to get rid of all those. And now we're just left with an n to the k, just like that. Okay? So that's a perfectly legit move to make right there. And the key here is that the total number of things that you have on the top that you're multiplying together, the n minus 1, the n minus 2, da 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 da, all the way to there is you have k of them. There's k of them right there. Yeah? Everybody buy that? Yeah, you should. Sorry to beat that dead horse even more, but this is important because I want you to believe that this is true, okay? So all I've done, I've just taken this and I've just rewritten it like this. This is exactly the same thing. We haven't done anything now. Now what we want to do is show that this is less than something. In other words, we want to make this thing bigger because we're trying to find an upper bound, right? We're trying to find this. And so now that we've gotten here, I'm thinking, how could I, okay, so we have, and really what this is a sum of fractions, right? Like for each one of these k's that I plug in, it's going to look different, but in general, like, I mean, I'll just go ahead and write this. I don't want to write it out. Just imagine, right, we have 0 up to n, so we have n plus 1 of these things that we're just adding. We're saying that this thing is equal to something plus something plus something else, all the way up to the last one where we plug in an n right there, right? And for each one of those, it looks like this, right? And so I'm just going to pretend that we're just dealing with one of them, right? Instead of writing every single n plus 1 of them out, I'm just going to say, okay, well, if they all look like this, then I can manipulate this thing right here. And if I make that term bigger, it will make each one of the sums bigger as well. Does that make sense? I hope I don't need to go into that. So let's do that. Let's take this term right here. How can I make a fraction bigger? Like we talked about last time, there's two ways. You make the denominator smaller, or you can make the numerator bigger. I'm going to choose to make the numerator bigger. And the way I'm going to do that is I'm going to say, and in fact, I think I did this in the last one, right? We got to this point and I said, well, if I make this one bigger by 1, right? So what I'm saying here is this is my setup. I have an n, I have an n minus 1, I have an n minus 2, I go all the way up to n minus k plus 1. And what I'm going to do is say, well, that's less than or equal to, the n I'll just keep. And now I'm going to add 1 to this guy right here. And so I'll times that by n. Now I could add 1 or I could add 2 to that guy and I'll have a n right there. And then I keep doing that all the way up to this last one. So we go up to the last one. And now I'll add k minus 1 to this guy to give me an n. Okay? And if that's true, well, which it is, obviously, right? So like if I had 5 times 4 times 3 times 2 times 1, I could say that's less than 5 times 5 times 5 times 5 times 5. That's all I'm doing right there, right? If we were using actual numbers, like if I had a 5, 1 over 5 and stuff like that, it might be a little bit easier and I could actually write that out and we could do that with each one of these things, right? Because this is a sum of n plus 1 things. But it should be pretty obvious that this is going to work. We're doing this with every single term here in the sum, right? And yeah, if you add however many things up to this one, that has to be the case, right? And so if that's the case, it's also true if you put that over some kind of denominator like this. Yeah? Yeah, okay? And since that's true, how many n's are up here? Well, how many things are up there? Oh, there's k of them. Oh, right. So this is the same thing as n to the k over k factorial n to the k. This is why I dropped this hint like 5 times last year, because this is key here. You can say, wait a second, that's less than that, but that's oh, look at that. Those guys cancel. Okay? So let's be explicit here. Let's be explicit. What I'm saying here is that this sum, I would write it right here, but it's going to get all compacted. Yeah, I'll write it right here, it'll be fine. Is less than or equal to the sum as k goes from 0 up to n of, now instead of k terms like this, I'll just say n to the k right there over k factorial n to the k right there. Okay, everybody buy that? I took every term in this sum and I made the numerator bigger. And so now we have something, so now this value, whatever that sum is greater than or equal to the original sum right there. Yeah, everybody buy that? Okay, so those guys cancel. That is equal to the sum as k goes from 0 up to n of, now we just have 1 over k factorial. How did I know to get to this point? I didn't, right? Like I said, I spent a very long time trying to prove this. This is eventually something I landed on, and when I got to this point, I thought, this is a way easier thing to deal with than this thing. So I feel like I'm on at least a decent path here, right? But now what? Well, when it comes to sums, right, anything in summation notation, when in doubt, write it out. So let's write this out. What is this? This is 1 over k factorial, okay? As k goes from 0 up to n. So that's the same thing as 1 over 0 factorial. You better know what that is. Plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus all the way up to 1 over n factorial. Now I'm going to make my life a little bit easier right here and say 0 factorial is just equal to 1. So 1 over 0 factorial is 1 over 1 is just 1. Okay, so I'm going to make my life a little bit easier and just rewrite that first term as 1. Ditto with this second term right here. Okay, 1 factorial is just 1. So 1 over 1 is just 1. And so I'm going to rewrite that as 1. And let's just double check that I haven't messed anything up here, right? We said this thing is that. Yeah. We just rewrote that. This is exactly the same thing, right? Yes. Okay, good. Then this was our the crucial step really here is we were able to say this is less than that. That's true. We've looked at that very well. That cancels to give me that there's no more n's. Now it's just 1 over k factorial. 1 over k factorial. 1 over 0 factorial is 1. 1, yes. And then 2 factorial. 3 factorial. Yes. Okay. So we are good to go right there. Now the question is, what do we do now, right? Well, we're trying to show that there is some real number that this is less than. And what I'm looking at is a sum. And it's an arbitrarily long sum, right? N could be 100 million. It could be a billion, right? It could be any big number. So what that makes me think of immediately is how we have a sum. All we know is that it goes up to the nth thing. What methods do I know of to actually calculate a value for a sum? If at any point, if something has connected in your head while we do this, and you haven't proven this thing yet, but what I'm saying, you go, ooh, stop the video and try to work the rest of this out for yourself. Okay, this goes for the rest of everything in this video. If at some point you get something or you have an idea, please stop the video and attempt to go on with this. Okay? So what I'm hinting at here is really the only way we know that we've talked about how to compute an actual value for a sum is if it's a sum of a geometric sequence, right? Remember, if you have k goes from 0 up to say n of a to the k, right? That's what we're talking about here. So you have like a to the 0 plus a to the 1 plus a to the 2 plus all the way up to a to the n. We showed that this is the same thing as 1 minus a to the n plus 1 over 1 minus a, right there. Obviously, that's not what we're dealing with here, right? Like, we don't have something raised to some power getting bigger each time, right? But this is the only tool I know to actually calculate a number given something that looks like this, right? And so I'm thinking, you know, the point isn't to calculate what number this is, whatever it happens to be. The point is, I'm trying to get, if I could make this smaller than something that maybe I can calculate. And so, is there a way to do that? Well, so I'm going to put this away for a second. One thing I notice, and I think I'm going to switch to blue. I think blue looks better, does it? Let's try a different black, because this black seems to be fading. So, first off, this thing doesn't really fit a pattern, right? I'm seeing a pattern here. We have a bigger number, smaller number, smaller number. It keeps getting smaller and smaller. This thing kind of ruins the pattern. So I'm just going to focus in on this guy right now. And I'm thinking, okay, we have 1 plus, what's 1 over 2 factorial? Well, that's a half, right? And if I'm thinking about geometric series, a geometric sequence, yes, the sum of a geometric sequence, or a geometric series, right? The first thing when I see this, the next thing I think about is, well, you know, if this were a quarter plus an eighth, in other words, if this were 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 to the third up to any arbitrary number, then I would be able to calculate it, right? Because, like I said again, we've proved how to deal with something like this, right? We don't have that now, but we would like to get this thing less than, and you know what? This does look like it's less than that. What do I mean? Well, just give me a second here. Give me just a second. Again, if at any point you think you know what to do, stop and plug along here, right? Try to prove this. What I'm saying here is this is 1 plus 1 over 2. Now, 3 factorial is 3 times 2 times 1, which is 6. So this is a sixth. The next one would be 1 over 4 factorial, which would be 4 times 3 times 2 times 1, which is 4 times 6, which is 24. Right? The next one would be 1 over 5 factorial, which would be this times 5, which I think is 120. And so on and so forth, right? And it does indeed look like this is a smaller number. It looks like, right? So this is, and like I said, we're forgetting about that plus 1 right there. It does look like this part, at least, right here. So this is true so far. 1/6 is smaller than 1/4. And 1/24 is obviously smaller than 1/8. 1/120th is obviously smaller than 1/16. Plus, and so on, all the way up to the 1 over n factorial, and then we'll have to figure that out. But right now I'm just thinking, like, I'm just trying to get my head around this. And what I'm seeing here is we have a 1 half squared, 1/2 to the third, 1/2 to the fourth, and so on. And this is where I'm saying, now, in order to prove that this is indeed the case that this thing is less than this thing that I'm figuring out? Don't forget your +1 at the front. Now we're going to need some induction to prove that. Okay, but this does look like it works, doesn't it? So, in fact, what I'm going to go ahead and do is just figure out what this should be. Then we'll work out to make sure that this does work. So bear with me here, okay? So let's just start with this line here. I'm going to say, yeah, I think this is right. This should be less than or equal to, I'll keep the 1 there, and now we have 1 plus a half plus a half squared plus, and let's put a couple more up here just so this would be 1 over 4 factorial, 1 over 5 factorial, all the way up to 1 over n factorial, okay? So yes, this, like we just saw, that is less than that. 1 over 4 factorial is less than 1 over 2 cubed. 1 over 5 factorial is certainly less than 1 over 2 to the 4th. And so now the question is, okay, 1 over 2 to what power? Well, when it's 2 here, the power is 1. When it's 3 here, the power is 2. When it's 4 here, the power is 3. When it's 5 here, the power is 4. So when it's n here, the power is 1 less than n, or n minus 1. Now we need to prove that, okay? And this is the point I was saying. If you just wrote this, you're good, because it's true. It's obviously true, right? Like, how could it be any other way? But if you wanted to be completely rigorous, we would need to prove this. We're going to do that right now just to make sure that we can, because this is a pretty big thing. At least I've made it into a big thing, you know. Like, I want to make sure that I have not just messed something up, right? So, obviously this part works, but what about this part here? Is it the case, this is what I'm trying to see here, is it the case that each one of these, 1 over n factorial, is that indeed less than or equal to the 1 over 2 to the n minus 1 factorial? 1 over 2 to the n minus 1 factorial. That's what I want to show. If I could show that that's true, then this step is absolutely, then I'm 100% certain about this step. And it's looking like we're really close, right? So I want to make sure that that works. So let's just see. What can I do with this? Well, this is the same thing as 1 over n factorial less than or equal to 1 over 2 to the n minus 1. Okay. How about we bring these guys up? And I'm going to say 2 to the n minus 1 less than or equal to n factorial. Is that true? Probably. Let's see. So, and this is where you might want to use induction, right? I'm going to say, okay, what happens when n, because, again, if this is true, then this is true. Okay, so if I could show that this is true, then I get this, and therefore I get this line, which is really, really important here. So is that the case? Well, let's try induction. So I want to show that 2 to the n minus 1 is less than or equal to n factorial. So I'm going to say, okay, theorem that we use proof by induction. And this is just scratch work right now, okay? At the end, we're going to put all of this together and we're going to make it look nice, okay? But right now, this is just my scratch work. In fact, as we're doing this on a piece of paper, I'm using another piece of paper to just check myself and say, is this legit? And so, okay, I guess base case, n equals 0. Although, n can't equal 0, can it? Let's think about the context here. We're not trying to, n doesn't need to equal 0. So, I guess my base case would be n equals 1. So let's try it. When n is equal to 1, we have 2 to the 1 minus 1 less than 1 factorial. Is that true? 2 to the 0, is that less than or equal to 1? Well, that's 1 less than or equal to 1. 2 to the 0 is 1. 1 factorial is 1. So yes, it's true. It holds in the base step. Yeah? Okay, you make some room here. Okay, so base step holds. And just to be sure, I'm going to take another step. Let's just see. Let's just make sure. Because sometimes the base step will hold, but nothing else will, right? So let's just see here. I just want to make sure. What about when n is equal to 2? Of course, you do not need to do this, but we're going to try anyway. So 2 to the n minus 1 would be 2 to the 2 minus 1, less than or equal to 2 factorial. That's 2 to the 1, less than or equal to 2 factorial is just 2. 2 less than or equal to 2? Yeah. I want to see it actually getting bigger. I would feel better if it actually got bigger. It's always equal. So you don't need to do this. This is not induction, by the way. This is just me being a nut job. 3 minus 1 less than or equal to 3 factorial. Is that true? Well, is 2 to the 2 less than or equal to 3 factorial? 2 to the 2 is 4. Is that less than or equal to 3 factorial is 3 times 2 times 1, which is 6. Ah, now it's getting bigger. Now I feel better about this. Because my intuition here, when we actually wrote these guys out, was that these guys get really, really small. In other words, the denominators get really, really big, right? Right here we're at 120, but 2 to the 4 is 16. So I'm feeling like, okay, yes, this is what it should be. So base step is not just done, it is destroyed. The base step holds, okay? So now let's do the inductive step. Suppose it's true all the way up to k. So suppose that k minus 1 is less, 2 to the k minus 1 is less than k factorial. And we must show that 2 to the k plus 1 minus 1, or 2 to the k, is less than or equal to k plus 1 factorial. That's what we must show here. That's my goal. So given that this is true, can we show that this is true? Well, I don't know. Let's try here. Notice here, and this is kind of nice that I already did this, when k is bigger, because we've already done it when k is equal to 1, right? We also did it when k was equal to 2. We also did it when k was equal to 3. So now I can just go ahead and say, well, when k is bigger than or equal to 3, you'll see why that matters. So when k is bigger than or equal to 3, then what can we do here? Well, I can make this thing look like this by multiplying that by 2, right? Because 2 to the k minus 1 times 2 is equal to the thing that I'm trying to show, 1/2 of the thing I'm trying to show. But in order to do that, I would need to multiply this guy by 2 as well. Yeah? Yeah, I just took the original thing that I'm supposing is true, multiply that guy by 2. And now we have 2 to the k less than or equal to 2 times k factorial. But since k is bigger than 2, then this thing must be less than, and I mean, obviously, but what I'm saying here is that's less than this thing, which is less than this thing, and so on and so forth, all the way up to k times k factorial, which is less than or equal to k plus 1 times k factorial. But k plus 1 times k factorial is k plus 1 factorial. So we have on this side, 2 to the k is less than or equal to k plus 1 factorial. That's what I needed to show. That's what we showed. This is kind of nice that I went above and beyond, because now I don't need to worry about, well, what about when k was 0? What about when k was 1? It's not technically less. It's just I just went for broke and said, well, now k could be really big. We're going to do that later in just a minute, but you'll see there's kind of a method to my madness here. Now we don't need to worry about it because we've already checked and we've said, yeah, okay, it's big enough. Don't worry about it. And when it's even bigger than that, then you get, multiply both sides by 2. That thing has to be less than if you multiply that side by k plus 1. Okay? So, yeah, indeed. So, therefore, 2 to the n minus 1 is less than or equal to n factorial by mathematical induction. But that means that I divide both sides and I get 1 over n factorial is less than or equal to 1 over 2 to the n minus 1, which is the same thing as 1 over 2 to the n minus 1, which is what I wanted to show. And so now, yes, since this is true, then this is true. And it's true for each one of those, right? It's one way you could do it. I do want to take just another minute to kind of... So maybe you didn't think to do an induction proof for that. What else would be acceptable? Well, one thing you notice is like each time here you're stacking on a 2 to get to the next term. You just multiply the denominator by another 2. But each time here you're multiplying the denominator by a bigger number. So I mean, you could, if you really wanted to make this argument that this thing is less than or equal to this thing, you could have done something like, well, since 1 over 2 is less than or equal to 1 over 2, then it must be the case that 1 over 2 times 2 is less than or equal to, we're going the opposite way now. 1 over 2 times 3 is less than or equal to 1 over 2 times 2. Since that's the case, it must be the case that 1 over 2 times 3 times 4 is less than or equal to 1 over 2 times 2 times 2. Or you could have done it the opposite way and said, okay, 2 is less than or equal to 2. And so 2 times 2 is less than or equal to 2 times 3, obviously. Therefore, 2 times 2 times 2 is less than or equal to 2 times 3 times, I'll just multiply by a bigger number. Therefore, 2 times 2 times 2 times 2 is less than or equal to 2 times 3 times 4 times 5, and we get what we want, right? Which is that 2 to the n minus 1 is less than or equal to n factorial. Which then you flip the guys around or you bring down to the denominator and you get the thing that you're trying to prove, which is that yes, this thing is less than that thing right there. When we write this up, I am going to include that induction proof that we just did, but I'm going to put it outside of the big proof. We're not going to start going through and doing all this and then just stop and do a different proof. We're going to start off, before we do the proof, with what's called a lemma. And that's like a little theorem, right? It's not like the big thing that you're trying to prove. We call it a lemma, L-E-M-M-A. And we're going to start off our proof with that by saying, hey, here's it's called a lemma. It's like a little theorem. It's not worthy to be called a theorem because, like I said, if you just wrote this, I'd be like, good, yes, you noticed. It is indeed. This is bigger than that, right? So it's not really worthy of being called a theorem. We're going to call it a lemma, but we want to have all of our T's crossed and I's dotted. So we're going to start off with that, and then we're going to go into our proof. But anyway, here we go. Now we have a value that we actually can calculate, right? So notice this guy he's just going to have to hang out because we know how to do this part, right? This is some number raised to the 0. Some number raised to the 1, some number raised to the 2, and so on and so forth. This guy does not fit the pattern, so we have to be careful and keep him out. So I'm gonna rewrite this in summation notation and say, okay, this is the same thing as 1 plus, this is equal to 1 plus, now I could write that in summation notation and say that's the same thing as 1/2, rather, the sum of 1/2 raised to some variable, how about k, as k, because of this one right here has to start at 0, right? Starts here at 0, and goes all the way up to n plus 1. No, n minus 1, sorry, n minus 1. Now let's just check and make sure I haven't messed anything up here. We have a total of n plus 1 terms, right? the 1, the 2, the 3, all the way up to n. That's n of them. Then we have the extra 1, so a total of n plus 1 of them. Here in this part, I have 0 up to n minus 1. That's a total of n terms, which is weird because the 1 is the 1, the 2 is the 2, all the way up to the n minus 1 is n minus 1 of them. But then the 0 adds an extra 1, so you have a total of n, and then n plus 1. So, okay, I feel good about this. All right, this looks like the right way to go. And now I can actually calculate this value. Okay, so this is the same thing as 1 plus, we have a geometric series, a geometric sequence, right? A geometric series. And so this is the same thing as 1 plus, right? There's the 1 plus, the way we do this is we go 1 minus whatever the thing is, raised to the power of 1 bigger than this. So instead of n minus 1, it's just raised to the n. On the bottom, we have 1 minus whatever the thing is, right? Just like I said, if you have the sum, this k goes from 0 up to n, I'll use capital N so we don't get too confused, of a to the k. It's the same thing as 1 minus a to the n plus 1 over 1 minus a. And let's just check. I know that this is true. Does this match with that? So, yeah, you make the power 1 bigger. Or make that power 1 bigger. Yep, it goes up to n plus 1. So this, it goes to n minus 1. So 1 more than that would just be n. The bottom is 1 minus the thing, right? Whatever that number is. Okay, that looks good. How does that help me? What are we going to do with that? There's a few things. We could do this a couple different ways. One way you notice is, well, you have denominators inside of a fraction. We could multiply the top and the bottom of the fraction by the denominator. So I can multiply the top by 2 and the bottom by 2. And that would kill the well, it would kill that fraction. It would kill that fraction. So what am I going to do? Well, this is, again, if you do it that way, that's great. It will work. But what I'm going to do is just think about it like this. 1/2 to the n over, well, 1 minus a half is just a half, right? Yeah. And I'm going to go ahead and clean this up because this is going to be nice if I go ahead and do this. Instead of 1/2 raised to the n, why don't I rewrite that as 1 over 2 to the n? Everybody buy that? That is the same thing as that? Yes? Okay, we're good. 1 minus a half is just a half. You take something, divide by a fraction, it's the same thing as multiplying by the reciprocal. So, I'm going to carry this 1 over here, I don't want to lose that 1. 1 plus whatever the top is times the reciprocal. So that's 2 over 1, or how about just times 2? The 2 jumps in, okay? And so I have 1 plus, the 2 jumps over and hits the 1 and becomes a 2. The 2 jumps over, hits the 1 over 2 to the n, so we have 2 to the n. That's the same thing as canceling one of them out. I'm left with 2 to the n minus 1. So that's plus 1 over 2 to the n minus 1, right there. Yeah? Yeah? Are we there yet? I think we're there, because that's the same thing as 1 plus 2 is 3, plus 1, oh, minus. You didn't catch me. Why didn't you say something? That should have been a minus. You guys. There we go. Now, what do we do with that? Now, you might be tempted, especially as you get into calculus, you're going to be tempted to say, well, in the limit, this thing goes to 0, right? But that's not what we're dealing with here. We're not talking about limits quite yet, right? We just want to show that there's a real number. That's that. But look at what we've done. 1 over 2 to any power is some positive number. So you're taking 3, and you minus off some positive number. Well, that's less than, I'm saying, or equal to, and we'll talk about that in a minute, if you just didn't minus it off in the first place, right? I mean, this should not, I can't believe I'm about to write this, but 1 over 2 to the n. Is that indeed Is that indeed the case? Right? Yeah, obviously. And the way I think about it is, well, if I didn't minus it off in the first place, then it would have been, 3 would have been bigger had I not minused that off. But we could be really pedantic here and say, okay, well, let's add the fraction to both sides, and we get 3 plus 1 over 2 to the n. Oh, that should be a minus 1, whatever. Subtract 3 from both sides. 0 less than or equal to 1 over 2. And yeah, since 1 over 2 to the n minus 1 is always a positive number, since that's true, then that must be true. Therefore, that must be true. Therefore, yes, 3 minus 2 to the n minus 1 is indeed less than or equal to 3. And therefore, 1 plus 1 over n raised to the n, which is equal to that stuff, is less than that, which is less than that, which is equal to this, right there. It is equal to that, and therefore less than or equal to 3. That is what we wanted to show. Now for the hard part. If you just try to use the binomial theorem right now, good luck. It gets so hard because on one hand, like I said, you're going to have, with the binomial theorem, this as a sum will be n plus 1 things. This will be n plus 2 things. So you're like, oh, that's good, right? But then you have to show, the funny thing is they both start with 1, right? And then, and so the ones on the right you have to show are bigger, but they're actually smaller. It's hard. It's really hard to do. And so, like, you could mess around with binomial theorem here for a long time before you remember another hint I gave you, which is maybe try to rewrite these things. And so, one way you could rewrite this, right? This is the same thing as n over n plus 1 over n, right? N over n plus 1 over n, which is the same thing as n plus 1 over n. So maybe I'll just try that. I don't know. N plus 1 over n raised to the n. Okay. Ditto right here. This is the same thing as n plus 1 over n plus 1 plus 1 over n plus 1. So it's a common denominator of n plus 1. Then we have n plus 1 plus 1 on the top, or how about n plus 2 on the top? Okay. So that's the same thing as n plus 2 over n plus 1 raised to the n plus 1. One thing I want to say is when I was doing this, like, I'm about to take a bunch of steps. And each thing I write is going to lead me to where I want to go. I don't want you to come away from this thinking that every one of these steps that I'm going to take, that I was able to see and go, oh yes, obviously this is the way I should go. Rather, what happened is that I went from here, well, first off, here I tried like 20 different things. And then nothing really worked until I said, well, let's try this. And then from here, I tried 5 different things. And the next step I'm about to take actually got me somewhere. And then at that step, I tried 5 different things. And it's only the next step that it actually worked. So what I'm getting at is, like, it's not like it's obvious that you should go from here to here. Or take the next step that I'm about to take. It's just that finally, what I'm writing actually led me to some decent fruit. So that's the way I'm writing this out. And so, okay, looking at this, what do we do? Well, I have no idea, but over here I have something to the nth power. Over here I have something to the n plus first power. So it's like I have a to the n less than or equal to b to the n plus 1. And I'm thinking, if I could get n, like if I have n things on one side, and if I had n things on the other side, then maybe I could get everything together. What would I have to do? Well, I have to pull off one of these, right? Why? Well, because if I do something like this, maybe this will help, right? Because then I could write this like this. Why? Well, because again, it's not like I was like, oh, from here I'll go to here. It's that I tried 1,000 different things, and it's not until I got to this point that I was like, ooh, this actually might give me something. So, again, that's what I'm going to do. I'm going to say, okay, if I could consolidate everything that's in powers of n on one side, maybe that'll make my life easier. So that's what I'm going to do. I'm going to say, okay, I'll keep this as this. So over n raised to the n. And then I'll write this as something to the nth power. And then that leaves me one of them left over right here. Okay? Now, I'm going to get everything to the nth power over on one side. Why? What makes me think that that's going to help? Well, because again, trying binomial theorem on both sides of this just led me to a bunch of heartache. So maybe if I can get everything all together and then raised to 1 power of n, then I'll have something, it'll probably be pretty ugly. But then I can use the binomial theorem on that only on one side of the equation, or the inequality, and maybe that'll help me out. So I'll divide both sides by this guy here. And I'll end up with n plus 1 over n raised to the n over n plus 2 over n plus 1 raised to the n less than or equal to n plus 2 over n plus 1. Now, what do we do? Well, the whole point was to get this as one thing raised to the nth power. And so, again, like I already wrote it like this a second ago. If I have two things like this, I could rewrite that like that. Why? Well, because I'm thinking one thing using the binomial theorem would be easier than two or more things using the binomial theorem. So maybe this will help. So I'm just going to try it and see. Say, okay, that's the same thing as all of this raised to the n. Okay, so what would that be? I guess n plus 1 over n all over n plus 2 over n plus 1. Maybe we can make that look a little nicer. So let's do a little work over here. N plus 1 over n plus 2 over n plus 1. That's the same thing as divide by a fraction, multiply by the reciprocal. That's n plus 1 over n times n plus 1 over n plus 2, like that. And I can multiply that together to give me n plus 1 squared over n times n plus 2. Okay, so let's go ahead and rewrite this thing as that thing right there. So I have n plus 1 squared over n times n plus 2 raised to the n less than or equal to n plus 2 over n plus 1. And again, each one of these steps, I tried like 20 different things. And it wasn't until I got to this that I was like, well, maybe, and rewrite it like this, maybe, and try a bunch of different things, But this is the route. This is the golden thread here that led me to something. Led me to an actual solution. Okay, so what do we do here? I don't know. Maybe multiply out the squared part. Okay. So let's do that. N plus 1 quantity squared is the same thing as n squared plus 2n plus 1. And that's over, and maybe I'll multiply this out. That's the same thing as n squared plus 2n, right there, all raised to the nth power, less than or equal to n plus 2 over n plus 1. Yeah? Yeah, looks right. Okay, well, and so now what? Boy, I don't know, but I think I would like to use the binomial theorem. And I know that the binomial theorem works a lot better if you have it as something plus something else. So, what could I do? Well, I can write that in a bunch of different ways. Look at that. That's that part and that. Maybe if I do this, maybe if I rewrite this maybe I'll split it up like this. So we have the numerator here, n squared plus 2n, and maybe I'll rewrite it like this. I could put that all over the same denominator, or I could split it up over the same denominator. And that denominator happens to be this thing right here. That's really nice, because that's just 1, isn't it? In fact, that's 1 plus 1 over n squared plus 2n. What told me that that's nice? In what way is that nicer than any of the other expressions I have here? Well, again, thinking about binomial theorem, I know that if that's a 1, then my expression that's going to be in the binomial theorem is going to be much easier to deal with if that's a 1. Yeah? Like, I mean, I could use the binomial theorem right here, and yikes, that would look really ugly. Or I could have split this up differently. I could have had n squared over n squared plus 2n plus 2n plus 1 over n squared plus 2n. Raise that to the n. And then my binomial theorem looks like this with my n choose k. And then I have my n squared plus 2n raised to the n minus k. 2n plus 1, n squared plus 2n to the k. Yikes, that looks terrible. But if I do it here, this thing is just a big fat 1, which is nice. And then this thing is even a little bit nicer too. So I'm thinking my intuition's telling me maybe this one, maybe I'll work with this and just see what happens. Okay? So again, it's not like I started here and said, oh, I need to turn it into this. It's that every step I took, I tried 1,000 different things. And it wasn't until I got to here that something actually happened. And let's see what that is. So let's get this. I'm just going to rewrite, because now, hold up. Whoa. What am I trying to do? Right? The idea is I need to show that this is true. But since this is the same thing as this, if I could show instead that this is true, then I'll be able to say, well, since this is true, this is true. Since this is true, this is true, this is true, this is true, therefore this, therefore this, therefore this, therefore this. I'm just double checking, are all of these steps reversible? And yes, they are. So, my new goal, instead of showing that this is true, my new goal is going to be showing that this is true. Then I'll be able to say, since this is true, boom, 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 that's true. That's what we want to show. So we have a new goal, right? This is what I want to show. And it turns out it's going to be slightly easier if I rewrite this guy here instead of n squared plus 2n, if I factor out an n from it, leaving me at n plus 2 right there. And again, it's not like, oh, I knew that, and therefore that's how I originally wrote it. No, it's that after doing this a bunch of different ways, I was like, it'll be easier if I rewrite this thing again. So that's what I'm going to do, right? This is what we're trying to prove, and we know that if we could prove this, then it's just a few steps to get to the actual thing we're trying to prove. So I'm going to rewrite this again and say, okay, this is what we need to show. n plus 2 right there. Okay? Okay, now what? The exact same trick that we used last time. You'll see, right? Now, why is my intuition telling me that? Well, because we have a very simple thing. 1 plus something raised to the power of n. That's very easy to deal with. Now let's do this in black. Here we go. So, over n times n plus 2 raised to the n by the binomial theorem is equal to the sum as k goes from 0 up to n of n factorial k factorial n minus k factorial times 1 over n times n, was it plus 2? Yep, plus 2 all raised to the k. You could do it with n minus k. It's still true if you do it with n minus k. It's just going to be harder to deal with. And right away, I notice, well, let's rewrite this, just like we did last time, right? Instead of writing that as to the kth power, I could write that as 1 over n to the k. Well, what I'm doing here is n plus 2, raising that to the k, and saying that's the same thing as n to the k, n plus 2 to the k. Again, how did I know to do that? Well, because you're not seeing the 20 other steps that I took before I actually got to that point, right? So, right, I'm just going to keep that up there. We'll rewrite that as the sum. This k goes from 0 up to n of n factorial, k factorial, n minus k factorial. Now, all that stuff's in the denominator, so I could just put it in the denominator, which is what I'm going to do. I'm going to say, okay, that's the same thing as n to the k, n plus 2 raised to the k power. Okay? Same trick we did before. Let's cancel these out. Okay, if I canceled those out, what I would be left with is the sum. As k goes from 0 up to n. That does not look like a k. Now it looks like a k. So, what's left on the numerator? Well, n minus 1, n minus 2, all the way down to n minus k plus 1. Okay. That n minus k is gone. We're left with that n to the k, which, oh, remember what we did last time? Maybe it'll work again! But this time we picked up an n plus 2 to the k. What are we going to do with that? Well, we'll see. So, same trick as before, right? We're trying to show that this is less than something. Hopefully, we could just use some same tricks and then maybe something will pop out. I don't know, but let's just try the same trick, okay? We're going to say this is less than or equal to k goes from 0 up to n of, if I made each one of these bigger and made it n times all the way up to n's, k into the k, n plus 2 to the k. How many n's are up there? K of them. So that's the same thing as n to the k. So it's the same trick, right? Same trick as we did before. Those things cancel out. That's equal to the sum, this k goes from 0 up to n of 1 over k factorial, n plus 2 to the k. Now, again, I'm trying to make this less than or equal to something. And something I notice. It's like, if we didn't have that bad boy right there, if he were just gone, if you just gave me this sum right here and said, okay, k goes from 0 up to n of something over something else to the k, I would say, oh, I know how to compute that. I know exactly how to compute that. In fact, that was the aha moment a minute ago. Like, if you have something raised to the kth power, no matter what's in there, you know exactly what to do with that, right? You just take whatever that thing is, 1 minus 1 over that thing, raise it to the n plus 1, and you go 1 minus whatever that thing is, right? And so it's like, if that weren't there, I would actually be able to calculate this and see what it's equal to. So, is there a way of getting rid of that? Well, again, what are we trying to do? We're trying to, again, we're trying to show that this is smaller than something. So, maybe if I make this thing a little bigger, then what? How can we do that? How can we make this thing bigger? Well, we already made the numerator bigger. Maybe we can make the denominator smaller. I can make the denominator smaller by just not writing that guy. In fact, I could just say, like, and think about this now. And this is where we need to be a little bit, we need to have some discernment here, right? I could say, well, hold up. What if n was like 0? Or if n was 1? then it wouldn't be less than, because that would just be a 1 both times, right? When k is equal to 0, you'd have 0 factorial and some stuff plus 1 factorial, right? And you couldn't really say that that's less than, right? I mean, well, you couldn't say it's strictly, you could say less than or equal to, but just ignoring it entirely, right? And so what we could do, and what I think we're going to do, is this, remember, this is all just scratch work before we actually write down the proof. Is I think it would be good to note, just like I did with that short induction proof that we hammered out that we're going to actually do in the big proof, is that, you know, I won't need to worry about stupid cases like this if k is big enough. So what we could do is just say, well, we could take care of the case when k is equal to, well, I guess it can't really be, well, it could be 0. Here it could be 0, but you know what I'm saying? When n is equal to 1, our original thing that we're trying to prove right here, I could take care of all these silly cases where, you know, somebody could come along and be like, well, yeah, but what if your n is only equal to 1? Well, if my n is only equal to 1, then we have this scenario right here. That would just be 1 to the 1. This would be 1 plus 2 to the 2. Is that true? Is 2 less than or equal to, this would be 3/2 squared, which is 9/4. Is 2 less than 9/4? Yes, it is. And then they say, yeah, but what if your n is equal to 2? Well, okay, 1 plus 1 over 2 to the 2. Is that less than 1 plus 1 over 3 to the 3? And you get that 9/4 less than or equal to, what would that be, 4/3 to the 3? Which would be 27. 4 to the 3rd is like 64 or something. And yes, indeed, that's the case. So that's what we're going to start with in our proof. We'll say, you know what, let's just take care of the stupid cases. We've taken care of the stupid cases where n is equal to 1, n is equal to 2, and it's still, the thing that we're trying to prove is still true. So, when it's bigger than that, and now we can look back here and say, well, k is bigger than, the k is, you know, the n is going to be bigger than 3, so that we don't need to worry about, is this actually less than, or da-da-da-da-da-da. We could just say, we know that k is going to go up past 3, okay? Because we've already taken care of the case when k only gets to 3. So when k goes past 3, then it's certainly the case that this would be less than or equal to n of not having that in the first place. If we just had this right there. Now, is that true? No matter what k is some number, some integer that's bigger than 1, right? Because, again, we're talking about the cases where it gets bigger than 1. We're not talking about the stupid cases. We've taken care of the stupid cases, right? We're talking about, eventually, this thing is going to get up to, like, 5. And when that's the case, okay, so we have some number down here and some other number there. Is it the case that that thing is less than not having it in the first place? Well, yeah, obviously. Multiply both sides and you get whatever's in there and your n and your thing. Right? I just brought this upstairs, brought him upstairs. The whatever that thing is cancels, and yeah, I'll just go ahead and do it. It's the n plus 2 to the k. 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 So whatever that is, and again, n is bigger than 3, so you don't need to worry about it being -2 or you dividing by 0. We've taken care of that. We don't care about that. We care when n is bigger than 3. When n is bigger than 3, that's a positive number, no matter what k is. You can divide both sides by it, and you get that this is that. And so yeah, if that were a k factorial, right, that would be a k factorial. That would be a k factorial, which is always bigger than or equal to 1 anyway. So yes, okay? This is always true for k, for any k, all right? And so there you go, all right? But what's that? Ugh, yikes. Well, let me rewrite that. as the sum, as k goes from 0 up to n. That's the same thing as 1 over n plus 2 to the k. Now we know how to deal with this, right? This is just a geometric series, right? We have a formula for this. We say, okay, no matter what n is, no matter what's in here, we just take 1 minus whatever's in there and raise it to 1 power higher than n, so n plus 1, over 1 minus whatever's in there. What's in there? Well, 1 over n plus 2. Okay, n plus 2 over n plus 2. Now here's where I'm going to be a little bit creative and say, what am I going to do? Well, what's messing up my life right now is that I have denominators inside of a fraction. So if I kill that denominator right there, it might, I don't know, it might make my life a little easier. So I'm going to go ahead and do that. I'm going to say, okay, I want to kill that, so I need to multiply this thing by whatever's in that denominator, which is n plus 2. Whatever I do to the bottom, I got to do to the top. So I'm going to do that on both. N plus 2 right there. Okay. He distributes over and gives me, this is equal to, he distributes over 1 times it is n plus 2 minus, right, there's my minus. He jumps over, and now we have n plus 2 over n plus 2 to the n plus 1, right? You see what I did? I rewrote this as 1 over n plus 2 to the n plus 1. And then when I multiply him through, he comes up in the numerator. Which means that this is very similar to last time, isn't it? This cancels with one of these, leaving me 1 over n plus 2 raised to the nth power. Okay, what happens in the denominator? Well, he jumps over. Okay, so I have n plus 2 minus what? Well, n plus 2 jumps over. Oh, he kills the n plus. Oh, yeah, that's the whole reason I chose n plus 2 in the first place. So that's gone now, and I'm just left with a 1. Okay, all right, that works. Works. Well, what's that? I don't know. Well, I don't know. Maybe I'll rewrite the denominator so it looks a little nicer. N plus 2 minus 1 is the same thing as n plus 1. On the top, I have n plus 2 minus some number. Oh, wait, hold it. That's what I'm trying to show, isn't it? Luckily, this number is a positive number. And just like last time, I have a numerator and I subtract a positive number off of it. That is less than if I had never subtracted anything off in the first place. That would be less than if I didn't subtract from the numerator. If I just left it as n plus 2 over n plus 1, which is what we wanted to show. Let's just double check that. We have our expression, which we derived wildly. How did we get there? I don't know. It's not like I knew that I was going to get here and that this was going to pop out. No clue at all. It's that I messed with the original thing until I got to here. I was like, what can I do with this? I don't know. This. Let's use the same trick that we did before. Okay, we'll use the same trick. And we get this. And we get wait a minute. So then there's, well, I'll just say it. So yeah, that is less than that. Okay, cool. I can actually calculate that. Well, let's see what happens. No way. No way. And it turns out to be like exactly what you need it to be. And look at that, right? Make n really, 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 really big, and it gets just close enough. It's just exactly what you need it to be. Huh. How about that? I didn't know when I first started off doing this that was going to pop out. I didn't know that I needed to get to this point. It's that I tried a bunch of things, and this eventually got me to something that I needed. And so, this shows that this is indeed true. And from that, we'll be able to derive the actual thing that we want. We're going to start here, show that this is true, and then from here, since we have that that's true, we'll rearrange until we get the thing that we're trying to prove. We're going to put all this together now, okay? But since we, like I said, if we're gonna need this right here, and this is what I said we're gonna call our lemma, lemma number 1, which is for all integers n, where n is bigger than 1 or equal to 1, then 1 over n factorial is less than or equal to 1/2 raised to the n minus 1. And this is just a stylistic thing. This seems, you have, as you saw, you have the thing you're trying to prove, and it's just beautiful. Like you have the thing and you use binomial theorem and this and this and this. You don't want to stop in the middle of that and be like, oh, and by the way, this and that. So we're going to put it outside of our proof. And then when we're doing our proof, we'll just say, by lemma 1, this thing's less than that thing. It'll look much nicer. And it's not just that it'll look nicer, it's that, remember, we are trying to communicate an idea from one brain to another person's, or one person's mind to another person's mind, right? And so it's nice to not have to break up that thought process and say, oh, and by the way, here's this. So we're going to get this by the way thing out of the way before we actually go into the bread and butter of what we're trying to do. So, lemma, this, proof. We do induction on n. Okay? Base step. When n is equal to 1, then, now let's think about how we did this, right? We had the 2 on the one side. So 2 to the n minus 1 is less than n, less than or equal to n factorial, right? That's what we need to show. So when n is less than 1, then 2 to the 1 minus 1 is less than or equal to 1 factorial. So 2 to the 0 is less than or equal to 0, less than or equal to 1. And so 1 is less than or equal to 1. Okay, so let's do it this way. So I'm sorry, I wrote this out. We should start here and say, when n is equal, let n equal to 1. Let n equal to 1. Since 1 is less than or equal to 1, then 2 to the 0 is less than or equal to 1 factorial. And so 2 to the n minus 1, which is 0, is less than or equal to n factorial. Yeah? Yeah, okay. So the base step holds. Now the inductive step. Suppose that for k bigger than 1, this is true. 1 over k factorial is less than or equal to 1 over 2 to the k minus 1. We must show... Oh, I'm sorry. The base step doesn't hold yet. I'm sorry. So the base step doesn't hold, but this implies that 1 over n factorial is less than or equal to 1 over 2 to the n minus 1, which means the same thing. In fact, these all mean the same thing. That means the same thing as 1 over n factorial less than or equal to 1 over 2 to the n minus 1. Yeah, and so base step holds. Sorry about that. Okay, so base step holds because we want to, yes, that implies that we want to be explicit, right? We're saying, let n equal 1, and now you got this, but what does that have to do with that? Oh, please show me. Be explicit about this. Yes, okay. Since that's true, this must be true. That's what you wanted to show in the case where n equals 1. Okay, so now what about when n's bigger than 1? Well, we're going to bring in a new variable called k and say, well, when k is bigger than that, now maybe k is 2, k is 3, k is 4, suppose that this stays true. Okay, and what are we going to do? Well, I'm going to do the same kind of thing that I did here and say, well, first off, now we must show, and I'm going to go ahead and put this over here, must show 1 over k plus 1 factorial is less than or equal to 1 over 2 to the k. Now, that's what I need to show. Okay. By the inductive hypothesis, right? That's the inductive hypothesis. By the inductive hypothesis, 1 over k factorial is less than 1 over 2 to the k minus 1. Yeah, because that's what that means. That's the inductive hypothesis. So, and I'm just going to save myself some room and just do it on this line. So, 2 to the k minus 1 is less than or equal to k factorial. Right? But since k is bigger than 1, k is either 2, so since k is bigger than 1, then 2 is less than or equal to k. Yeah? K is an integer, right? We only do this with the integers. So it must be the case that k is bigger than or equal to 2. Now I could say, well, since that's true, I could say, well, okay, that's true. So I'll just multiply this. Then 2 times 2k minus 1 is less than k times k factorial. Yeah? Because that's true. That must be true, right? Or rather, this being true and that being true means that that's true. But if that's true, obviously, that's also true. Yeah? Yeah, has to be. But this is the same thing as 2 to the k. And this is the same thing as k plus 1 factorial. So that must be the case. K plus 1 factorial. Dividing both sides, or bringing these guys down, we get k plus 1 over here. Here we get 1 over 2 to the k, which is the same thing as 1 over 2 raised to the k, which is what we wanted to show. Thus, that must be true. 1 over n factorial is less than or equal to 1/2 to the n minus 1. The end. So that proves our lemma. The moment we've all been waiting for. Theorem. There exists a real number, e, such that the limit as n goes to infinity of 1 plus 1 over n raised to the n is equal to that real number, e. Now, we could just dive right in and start with our calculations, but with a proof this involved, as you've seen, there's a lot of things going on here. It's really nice to tell your audience ahead of time what you're going to do. So that's what I'm going to do. I'm going to say, okay, proof. Here's how we're going to prove it. I'm going to tell you how we're going to prove it. Proof. We will show that the sequence, and I'll write it as we originally wrote our sequences, but in these brackets here, which is 1 plus 1 over n to the n. And here I'll even specify where n is bigger than or equal to 1. We will show that this sequence, the sequence 1, I'm going to use Roman numerals here, 1 is bounded above. I don't want to say bounded above because I think the last time we said has an upper bound. So we'll do that. We'll show that this sequence 1 has an upper bound. Means the same thing as bounded above. Has an upper bound, and 2 is increasing. Now that's not all I want to say. Like, You know how to put this together because we've been talking about this forever, right? But your audience may not know. They might say, okay, what is that? How's that going to help you? Let's be explicit here. How is that going to help us? And we'll say, okay, so we'll show that this sequence has an upper bound and is increasing. What does that do? Then, by the theorem in part 1, that is the video, part 1. Then, by the theorem in part 1, we know that the sequence, because it has an upper bound, we know that the sequence has a least upper bound. Call it L. And also from the theorem in part 1, that the limit as n goes to infinity of 1 plus 1 over n all raised to the n is equal to that least upper bound. And by that, this was something I didn't say explicitly, that the sequence has a least upper bound in the real numbers. That is, there is a real number, and so I'll just be a little explicit about that. Since L is a least upper bound, it is a real number. Thus, we can define E as L, that least upper bound. Okay? It seems pedantic, right? I mean, I said the same thing over and over again, but it's really good to be absolutely clear what you're trying to do ahead of time, because especially as you go on in math, your proofs are going to get crazier and crazier and crazier, right? There's going to be more involved, more moving parts. It's really nice, especially for somebody who's trying to grade your papers, if you tell them explicitly, this is what we're going to do, okay? So that's what I'm doing right now. I'm telling the person who's reading this, the other mind to whom I'm trying to communicate this information, this beautiful fact about our reality. I'm trying to communicate, like, I want them to know, like, hey, this is how we're going to get on the same page here. This is how we're going to flow. I'm going to show you that it has an upper bound. I'm going to show you that it's increasing, and we know that that means that it has a real number, that this approaches some limit. It's an actual real number, okay? And therefore it makes sense to say that there is a real number E. We're going to define it that way. So at this point, you have your paper, and you've written the lemma part, and you got to the end of the lemma. Then you wrote theorem, and you wrote what we just wrote on the board. Okay, right below that, this isn't necessary. In fact, like, we could get away with not even mentioning this at all, and it technically would be correct. But just so that when we get into the actual parts 1 and 2 that we're trying to prove, we don't want to have to, like, go and do some other stuff. I'm just going to make a note, just after what I just wrote there on the same piece of paper. I'm just going to say, and also I'm going to communicate why I'm saying this. I'm not just going to say note that something. I'm going to tell them to make calculations or to make our proof smoother. I don't know, is that a word, smoother? Whatever, who cares? To make our proof smoother, right? So just letting the audience know, like, just so we don't have to, like, jump in and, like, take a step and say, oh, by the way, this also works if k is only equal to 1. To make our proof smoother, note the following. That when n is equal to 1, we have 1 plus 1 over 1 to the 1 is equal to 2. When n is equal to 2, 1 plus 1 over 2 to the 2 is equal to 9/4. And when n is equal to 3, 1 plus 1 over 3 to the 3 is equal, I really don't want to mess this up. It should be 4/3 cubed, right? So that's over 27. 4 squared is 16 times 4 is 4 and a 2 and a 64. Yes, okay, so 64. Okay? So 64 over 27. Two is less than 3. 9/4 is less than 3. 64/27 is less than 3. Do you believe that? Let's see. Is 64 less than 3 times 27? 27 times 3 is 21. 3 is 6, 7, 8. 81 is bigger than 64. So yes, okay. Yes, that works. Okay. So what am I saying here? To make the proof super, note the following. Note that in these first cases, 1 over n plus 1 is less than or equal to 3 when n is equal to 1, 2, and 3. Okay, so it holds. In other words, I'm just saying it holds in the case where n is equal to 1, n is equal to 2, n is equal to 3. Again, this isn't necessary. It's just, I just want to knock this out in case somebody really wants to be nitpicky or something like that, right? And so in other words, it is bounded, right? So that's what I'm saying. The sequence is bounded. When n is equal to 1, 2, or 3. And since 2 is less than 9/4 is less than 64/27, which you could check, but it's enough to just say this, then 1 plus 1 over 1 to the 1 less than or equal to, and we'll keep those that way. 1 plus 1 over 2 to the 2. 1 plus 1 over 3 to the 3. So the sequence is increasing for n is equal to 1, 2, and 3. Technically, is it increase? We need to show with the fourth one, but whatever. Okay, so everything seems, this is all I'm saying is like, okay, this is good, okay? So sequence is increasing therefore. And so note the following, I've said all this. Why did I say all this? Just so later on I could say n is bigger than 3 if I need to. Like this is obviously the case when n is equal to 3, right? Or when it's bigger than 3. Again, not necessary. You could just say that. I'm just trying to dot all my I's and etc. Okay, now I've written, referring back to the thing that I'm trying to prove, I'm going to tell them this is what we're doing now. We're doing part 1, Roman numeral 1. The sequence has an upper bound. Okay, so we do it the same way we did before. Note 1 over n to the n is equal to the sum of k goes from 0 up to n of n factorial, k factorial, n minus k factorial, that's 1 over n to the k. That's just by the binomial theorem. Okay, I don't even need to state that. It just is. Okay, so that is the same thing as the sum as k goes from 0 up to n of n times n minus 1, n minus 2, all the way down to n minus k plus 1. K factorial. And remember what I did there. I said n to the k. Right? But that is less than or equal to the sum as k goes from 0 up to n of n to the k over k factorial n to the k. Those cancel. So that's the same thing as, that is equal to the sum as k goes from 0 up to n of 1 over k factorial. I promised I would say something about this. You might say, what's that you keep saying, and you've said a few times, you always use less than or equal to. But obviously, if you have any number, like 6 times 5 times 4 times 3, it's not less than or equal to 6 times 6 times 6 times 6. It's clearly, strictly less right there. Right? Yeah. So then you say, well, why do you have the equal sign right there? Why less than or equal to? Why can't you just say that we know that this thing is strictly less than this thing right here? Why do you have to have this equal sign? So, technically, with what we're doing, we don't need that at all. We could say it's strictly less than. And in fact, that would kind of make everything go nicer too, because, you know, I've talked about an increasing sequence, and I said technically the increasing sequence, it doesn't have to be strictly increasing, where it's a strictly less than or something like that. And so, the thing is, especially like right here at this step, we're not taking a limit right now. We're not going to let n go to infinity to prove what we're trying to prove. But clearly this is about taking a limit, right? The theorem itself says that this limit, as n goes to infinity, exists. And interesting things happen when you go to infinity. And when you go to infinity, this thing right here is not necessarily strictly bigger. We'll come back to this in calculus in just a second, right? Like, for instance, you might say 3 minus 1 over 2 to the n is strictly less than 3. Yes, it's true, it is strictly less than 3. But what happens if we take a limit? When you make n really, 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 really large, this thing goes to 0, and then the statement that you had no longer applies, right? So, what I'm saying is, in this case right here, like, we could, yes, and it is true that for any finite number n, this is strictly less than that. But it may, we don't know, it may or may not be if we take a limit. But again, we're not taking a limit, we're just trying to show that for any number n, this thing is less than 3. And that's true, and we don't need that. It's just, I am in such a habit, and especially when you do analysis, you get in the habit of keeping that equal sign in there, because when you may think, well, obviously this thing's bigger than that, if you end up taking a limit later on in your work, it may not continue to be strict, right? Just like what I said here. This is 100% true. It is 100% true that that thing is strictly less than 3 for any value of n. But when you take the limit, that no longer remains true. So a way to kind of hedge your bets if you're doing analysis is to just say, you know what, I don't want to have to think about it. Because if I take a limit, it might end up being equal. And in this case, it would end up being equal. Maybe something like this happens here. I don't know. It could be that when I take a limit, it's this. And again, we're not taking a limit in this proof. It's just that this is a really good habit. I don't know if it's good or bad. It's a habit that I got into when I got into analysis that I've just kept around ever since. And I think it's a good habit to have, that when you're doing something like this, you don't know what you're going to do. Maybe later on you take all of this work and plug it in somewhere else, and then you end up taking a limit. It would be nice if you haven't messed something up and said, oh no, that's strict right there, because when you take a limit, it may or may not remain strict. You might pick up the actual equal sign. So it's just, if you're wondering why I've been like, well, obviously that's bigger. Why have the or equals to? It's a habit from analysis, and it's actually a pretty good habit to be in. Anyway, so this is what's on our paper. The sequence has an upper bound. We do this, we do that. We say that thing is less than that because all of those right there. In fact, since we're writing this up for an audience, let's be a little explicit about the step that we did there. We said there's n times n of them. And then in the next step, if your audience is not with you, I mean, you could, but you know what this is. There's k of those. Okay, so we're going to say that's the same thing as the sum as k goes from 0 to n into the k factorial into the k. Right? We're just being explicit for our audience. K factorial right there. Okay? And then they should be able to figure out there's k of them. If they can't figure that out, yeah. So, okay, what is that? Well, like we did before, that's 1 over 0 factorial. 1 over 1 factorial plus 1 over 2 factorial all the way up to 1 over n factorial, which I'm going to rewrite as 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus all the way up to 1 over n factorial. Now here comes the part, and I'm going to say it by lemma number 1. See how nice that is? Like I said, that is less than or equal to. We keep the 1. 1 plus 1 over 2 plus 1 over 2 squared plus all the way up to 1 over 2 to the n minus 1. Right? It's nice. I didn't have to go off on some tangent and say, oh, by the way, blah, 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 blah. This looks much nicer, and you're still with the flow. And because we took care of that in a lemma before the proof, just state it. It's like, hey, you already read that. Oh, yeah, that's right. Oh, that's where that comes in. That's kind of nice. It's kind of cool. Okay, so now what is that? That's the same thing as 1 plus the sum as k goes from 0 up to n minus 1 of 1/2 to the k. And you check that. Is that true? Is that part the same as that? Yes, it is. Okay, and so that's the same thing as 1 plus 1 minus 1/2 to the n, because it's always 1 power bigger than your largest power there, over 1 minus 1/2, which is the same thing as 1 plus 1 minus 1 over 2 to the n, over 1/2, because I just went ahead and did that. 1 minus 1/2 is 1/2. Which is the same thing as 1 plus, now put the 2 up in the numerator, 1 minus 1 over 2 to the n times 2, which is 1 plus, it jumps over, gives me a 2, minus 1 over 2 to the n minus 1, which is 3 minus 1 over 2 to the n minus 1, which is less than or equal to 3. Again, it is strictly less than 3 for any finite n, but since we're talking about a limit, let's go ahead and do that, okay? Notice I'm not putting a box at the end of this, because this is just part of a proof. We haven't proved the thing yet. This is only one part. So the sequence has an upper bound. There's my sequence. And for any value of n, we could say, in fact, what we should have done is said, at the very beginning, we could say, for n bigger than 3, because we've taken care of the case when it's not 3, right? Because somebody being really pedantic could have said, well, you use this formula, but if it's only equal to 2, then it's equal, it's not less than... Just shut up, right? You don't get, like, that's not the point, right? You say if it's not equal to 3, then it doesn't work, it's actually equal, it's not less than... So that's why we did that. We're going to say for when n is bigger than 3, then your thing looks like this, right? And that's why I did this. Just so you don't have that one kid in the class who's like, but that's equal, it's not less. If it doesn't go beyond 3, that's why we're doing that, kid. Keep your mouth shut. Keep up. No, I'm sorry. It's just, yeah. Okay, so for n bigger than 3, this is equal to that, which is equal to that, which is less than that, which is that, that's the same thing, which is this. But by the lemma number 1, this value is less than that value. But that value right there collapses to this, which we could actually calculate, which gives us this, boom, boom, which is that value right there. But that value is less than or equal to the number 3. And so, and I'll just state this for my audience, so 1 plus 1 over n to the n is less than or equal to 3 for all n bigger than or equal to 1. Because remember the note at the beginning. Okay? That's what we wanted to show. That's what it means to have an upper bound. This sequence has an upper bound. This is the part that might throw off your audience a little bit. And you could be more explicit and start with saying, okay, let's use the definition of increasing and then this and that. I kind of like to do it every now and then, throw off your audience, because we're gonna start with the actual thing that we proved, and you're gonna go, what does that have to do with anything? And then we're gonna show how it connects. And I think that's kind of cool sometimes. Depends on how explicit you want to be. Knowing your audience is important, right? Like if I were teaching this in class, I would, if I were just giving you these notes, I would not do it this way. I would do it the way that we did it just a minute ago when we first derived how we're going to do this. But we're going to say, okay, so the part 2, we have to show that the sequence is increasing. And I'm going to say for n bigger than 3, because we've taken care of the finished cases, observe that 1 plus 1 over n plus 2 raised to the n. Remember, now you're like, what does that have to do with anything, right? And your audience might be a little thrown off. I think this is kind of cool. Again, if you're teaching a class, you don't want to start with this, but since this is a proof, start with something that's true. That's what we're going to do here. Again, know your audience. Okay, so this, okay, observe that this, I'm observing it. What do you want me to observe about it? Well, I want you to observe that it's equal to, by the binomial theorem, it's equal to k goes from 0 to n of n factorial over k factorial n minus k factorial times 1 over n times n plus 2 raised to the k. And your audience says, yes, yes, I observe that that is true. So you say, okay. This is also true. K up to n. We could rewrite this as n times n minus 1 times n minus 2 all the way down to n minus k plus 1 all over k factorial. The n minus k is what I just canceled there, okay? Then this we could rewrite as n to the k, n plus 2 raised to the k. But that's less than, here's the same trick, here's the trick, less than or equal to, k goes from 0 up to n of n to the k over k factorial, n to the k, n plus 2 to the k. The n to the k's cancel, and this is the same thing as the sum as k goes from 0 up to n of 1 over k factorial, n plus 2 to the k. And we could say that, you know, I'm not even going to say it. N is bigger than 3. N is bigger than 3, so don't worry about this guy. He is going to be less than or equal to, again, that annoying kid needs to keep his mouth shut because we're not talking about, well, what if it's only, if it only goes to 1, then it's actually equal. Why would you rewrite it? Well, because n is bigger than 3, so don't worry about it. Okay, so k is going to have to be bigger than 3. And so in this case, it's absolutely, again, if I weren't doing an analysis type thing, I would say, you know, it is strictly less than. But, yeah, that's not where we're going. I'm just out of habit, keeping that equals in there. Okay, this is the same thing as k goes from 0 up to n of 1 over n plus 2 raised to the k, which is the same thing as 1 minus that thing raised to the, now it's n plus 1, 1 minus that thing. What is that thing? It's 1 over n plus 2. But that's the same thing as, I'll go ahead and try to do it right here. 1 minus 1 over n plus 2. 1 minus 1 over, and I'm going to do it, n plus 2 raised to the n plus 1. That looks really terrible, but I've just, right? I haven't changed anything. I dropped parentheses here, rewrote that down there, okay? Now I'm going to go ahead and do my n plus 2 on the top and the bottom. Everybody agree with that? I haven't changed anything. It's still all equal. That's equal to that. That's equal to that. Yeah? Okay, okay, we're good. So now I distribute that guy over, and I get n plus 2 minus 1 over n plus 2. Now instead of the n to the n plus 1, one of them is canceled out, so it's only to the n. On the bottom, I get n plus 2 minus n plus 2's have canceled, I get 1. And so that's n plus 2 minus 1 over n plus 2 to the n over n plus 1. Which indeed, since n is bigger than 3, less than or equal to n plus 2 over n plus 1. And your audience says, who cares? What does that have to do with anything? So I'm going to say, okay, well, but hold up. We've shown that this is true. And you say, yes, it is true. So, 1 plus 1 over n times n plus 2 raised to the n is less than or equal to n plus 2 over n plus 1. Yeah? Yes. So that's true. Yes. Thus, I'll go ahead and do it. Try to fit it all in here, and we'll see. 1 plus 1 over n squared plus 2n to the n. Right? I just multiplied that out. Is less than n plus 2 over n plus 1. Now, on paper, I'd probably just keep going down straight, but just to save some, just so we can have this all on the board, I'm just going to start going this way, okay? So instead of going down to the next line, I'm going to do this, which means go down to the next line, okay? These things are equivalent, okay? So this is the same thing as n squared plus 2n over n squared plus 2n plus 1 over n squared plus 2n, all raised to the n, which is less than or equal to n plus 2 over n plus 1. Is that the exact same thing I just wrote? Yes, because that is 1. And so this is exactly the same thing as that. So I haven't changed anything. And so that is exactly the same thing as n squared plus 2n plus 1 all over n squared plus 2n raised to the n, which is less than or equal to n plus 2 over n plus 1. Yeah? Yeah, I just combined fractions, right? They had a common denominator. I put them over the common denominator, and now we have this numerator plus this numerator all right there. But that is the same thing as, that is n plus 1 squared over n times n plus 2 raised to the n, which, as we showed, is still less than or equal to n plus 2 over n plus 1. Yeah? Yeah. That's what that is. All right, let's double check. Hold on. Square that out. You get that. Yes. Multiply that through, and you get that. Yes, and it's still less than the thing that we proved that it was less than. Oh, yes. Okay, good. Now, that's where we need to remember how we did this. There is an n plus 1 over n and n plus 2 over n plus 1. Now, is that too hard for my audience? Is that too big of a jump? Let's just see. My audience was reading this and they're following. They're like, okay, buy that. That's what you just wrote. That's just, yeah, I buy that. I buy that. Yep, I buy that. Oh, well, then you could, hopefully your audience, if they're reading this, they should be able to say, wait, how did you get from here to here? And then they could just say, well, you flip that. Oh yeah, the n plus 1 that's in the denominator would come up into the numerator to give you n plus 1 squared. Yes. That n that's in the denominator would stay in the denominator. And that n plus 2 that's in the numerator, when you flip it, would go down into the denominator. So yes, this is true. If I gave you this, you would be able to derive this. So I feel confident that you would be able to do that. Okay. That means exactly the same thing as n plus 1 over n raised to the n over n plus 2 over n plus 1 raised to the n is less than or equal to n plus 2 over n plus 1. Yeah? Yeah. Which means the exact same thing as, if I bring him up into the numerator, n plus 1 over n raised to the n is less than or equal to n plus 2 over n plus 1 to the n times n plus 2 n plus 1. Right, I just took what was in the denominator, brought him up to the numerator, right there. That's the exact same thing. Okay. And so, this means the same thing as n plus 1 over n raised to the n is less than or equal to n plus 2 over n plus 1 raised to the n plus 1. Because we had the same base here, right? N plus 2 over n plus 1, n of them, and then you multiply one more of them in, and it gives you that guy right there. Yes, that's true. But that means exactly the same thing as 1 plus 1 over n raised to the n. Yeah, that's what that is. That's the same thing. Is less than or equal to, and I'll be a little bit more explicit for my audience here. I'll say n plus 1 over n plus 1 to the n plus 1. Which means 1 plus 1 over n to the n is less than or equal to 1 plus 1 over n plus 1 to the n plus 1. Which is what we wanted to show. This sequence, whenever n is bigger than 3, this sequence is increasing. And we already saw that it's increasing when it's 1, 2, and 3. And so it continues to increase forever and forever and forever. Okay? And I'll just say, thus, the sequence is increasing. For all n bigger than or equal to 1. We don't need this part because we already told the audience at the beginning that once we get those things proven, we're done. And we'd probably just put our box there at the end. But I like to be, just like with the induction proofs, right? Like it's like you're done. You even said what you had to do and then you did it. And now you're going to restate it again? Yes, I'm going to restate it again, okay? It's just what I do, okay? And so, I'm going to say, since the sequence (1 plus 1 over n for n bigger than or equal to 1, since that sequence has an upper bound, as we've shown it has an upper bound, it has a least upper bound. Upper bound. L. And since it is increasing, the limit. Let's do it this way. Well, yeah. The limit exists, and the limit that I'm referring to here, the limit, 1 plus 1 over n to the n, is equal to that upper bound, L. Therefore, we may define E to be the real number L, which is the limit as n goes to infinity of 1 There we go. So I might want to reword this, because at the beginning we said that the number E exists. And I don't see the word exists, I see limit exists. And when you take calculus, like the limit exists, when you learn about limits, if a limit exists, it's unique, and that means that the number exists. So if this were a calculus class or an analysis class, this would be, well, this would be way more than enough. But maybe we want to restate this. We say, since it has an upper bound, we could say a least upper bound exists, right? And then saying that this is the E, that exists. But at any rate, I hope this was like the hardest thing that you've ever had to do in math. Because I think it's a really good exercise to have something that's to really try for a long time on something and feel like you get nowhere. Hopefully you got something out of it, out of that exercise. But more importantly, the whole reason I wanted to do this is because this little number here, which is approximately 2.7182881828459045, and so on, which is indeed less than 3. But this number is so important in calculus. It is, I mean, you could say it's like central to calculus, and not just calculus, but mathematics itself. But when we go into calculus, we're going to be using this function, e to the x, and it is so central to so many things that we're going to do in calculus that I wanted to have a very rigorous, solid foundation for this number that we're using. And you'll never see, before you take a class in real analysis, you will never see a proof that this limit exists. You just take it on faith, you know? And in a sense, I've still asked you to take it on faith, but I think I've shown you why we take it on faith, because it's just an axiom. There's just this axiom here. It's like, well, if it has the least upper bound, it isn't the least upper bound, because we just say so, you know. And that's just one of those things, and that's I kind of find that in and of itself interesting that we do that we can't say more than that. Like, how do you know that number does indeed, that this is a real number? Because we say so. If you have a limit, if you have a sequence and it's getting bigger, but you know it never gets bigger than this, then it hits a real number. How do you know it doesn't hit something else? Well, because we say so. It just does. There are no holes. Remember, like I said before, there's no holes in the real number line. Why? Because we say there aren't. And that's kind of interesting. But as you can see, that's kind of a deeper topic, or a more advanced topic that you're not going to see before calculus. You won't even see it in calculus. You won't see it until after calculus if you take analysis. And so I could see why you're not going to see a proof that shows that this thing exists, because it takes some bigger guns and some deeper theory. But I don't like that. And I didn't like it when I was learning it. It was like, you do this thing with this, and like we did in Algebra 2, we plugged in different numbers, right? We plugged in 1 plus 1 over 100 raised to the 100, and we got some value. Then we plugged in 1 plus 1 over 1,000 and raised that to the 1,000, and we got another number. And then we just went for broke, I think, and we did like 1 plus 1 over, and we did like a billion or something like that, and then raised it to the billion and got a number. And we could see that each time it gets closer and closer to this. It never starts getting bigger, right? So we had this idea that what was happening was that these numbers were kind of getting closer and closer to some value, and we just said we're going to call that value E. But we never saw that, yeah, indeed it does flatten out, and it never gets bigger than a certain value. Well, now we've shown, it's using elementary methods, really. I mean, you could call the binomial theorem not elementary, but it is. We're not using calculus, and that's what I wanted to do. I wanted to show that this number exists without using calculus, because this is central to calculus. And that's one thing that really drove me nuts when I was taking math, was like, we're just going to assume this thing exists. And then later on, it's like, how do you know it exists? Well, because of calculus, you could use calculus to show that this works. And it's like, yeah, but didn't we need this before we developed calculus? Yeah. Well, then how do you know this isn't just circular, right? Like, if you're using, because in order to, you could show that this number exists using calculus really easily, but you need the number E to show that. So it's like, you need something to show that it itself exists. And so we needed to find a way to prove this. Like, it sure looks like it's getting bigger. And it looks like it's never getting bigger than some value. How could we do that? Well, the way we just did. We showed that it was increasing. We showed that it was bounded. But that's in itself not enough. We need an axiom to show that, and that's why they don't do this in a calculus class or in a pre-calculus class, because you need the weird analysis stuff where we just say, yeah, it's a least upper bound. And so it makes sense that they don't, but it bugs me that they don't, because then if you don't have this, what we just proved, by the way, thin, right? Thus done. If you don't have that, then it's just circular. And it's like, well, how do you know that this thing doesn't blow up? Well, because you use the exponential function and blah, blah, blah. But we can't use the exponential function to show that the number that you're trying to do is that. And so I really wanted to give us a rigorous footing for this. We had to have some kind of weird axiom that's just like, okay, I'll take it. But I hope that axiom makes sense in the same way that I think I talked about before. You have two numbers, A and B. One of three things must be true. Either A is less than B, B is less than A, or they're the same number. That's an axiom. You can't prove that. It's just like, well, yeah, all numbers have that property. And you just say, well, yeah. Hopefully this feels the same way. That, like, it's increasing. Yep, it's always getting bigger. But it never gets bigger than something. Well, then it has to approach some number. Right? Yeah. And so we just say, yeah, that's an axiom. We'll use that. Now we've used that rigorously, and we've seen for certain, there should be no question in your mind now, that yes, this sequence does increase. Yes, this sequence is bounded, and therefore it approaches some real number. And we are going to define that number as E, Euler's number.